All right, let's go ahead and get started. So today we're going to talk about your next core, I'm going to call it core data structure. Really, your two core data structures so far have been arrays and linked list, because a stack and a queue is a data structure, but it's built mainly off of an array or a linked list. The next one, which you'll be used to implement other interfaces, are binary trees, which is basically another way to organize data so that searching is pretty much intuitively faster. Now, before I continue, real quick, I did catch up on grading all your labs. So all the labs up to today are correct inside of Blackboard. And when I say grading, I really just mean entering the grade and double checking your labs on Blackboard. Because the autograder, as you pretty much can tell, what you get in the autograder, chances are, is what's going to reflect on Blackboard. Rarely is there going to be a change. Because most of the time, if you can get past the autograder, you did everything else correctly. Okay. And then your projects, I'm still working on them. There's a lot to go through, so just sit tight. Hopefully I'll have that for Thursday. So yeah, let's go through binary trees. Hopefully it gives us a nice picture. No, it's going to say an overview. That's great. Definition, we don't care. Hey, a picture, perfect. Good. So, it is a tree. With a tree, you start at the root, just like a regular tree, except when we draw, the root's on the top and not on the bottom. All right, everyone okay with that? Okay, good. So you have your root node, in this case A, and it's going to have two children. Good morning.
Two children. Good morning.
Two children. Yeah, in the binary tree, you only have two children, or two or fewer, I should say. So A has two children, B and C, and then D has two, well actually D has one child, G, and then G has no children because he points to null. This little symbol they use to represent null. So just make sure everyone's paying attention. How many children does C have? All right. And how many does H have? None, or zero, right? And then B has how many? Two. B has two children, D and E. Yes?
Do we decide which child ends up having more and more children as it goes on? So do we decide?
In a binary tree, you only have 2, 1, or 0. Oh, but how are we going to populate this?
Could we make it to where both B and C only have one, or does it have to be like a certain way?
Depends on the binary tree you create. So one thing about binary trees is there are many different ways to organize them. But as a high-level binary tree, simply you have a root node, and every node has at most two children. And that's really the end of the definition of a binary tree. But we're going to, of course, add some stipulations to it in order to gain some performance improvements later on. Okay, but before we go on, again, binary trees. I'm trying to, the slides, and I think the slides do a good job here, we're trying to harp on the fact of what a binary tree is versus other types of trees. So for it to be just a binary tree, again, you have to have at most two children. So these 4 examples are binary trees. The first one has 1 node with no children. The second one has 2 nodes, where B is a child of A. And also the second one also has 2 nodes, but it's the right child and not the left child. It doesn't matter which side it's on, it's still a binary tree. Good morning. And of course the last one has 3 nodes, and it's A has 2 children. What are the other ways to write the binary tree that's on D that's still legal, or still a binary tree?
A to C and C to another one?
C to B or to D or something, yeah. So you could have, let me use my mouse pointer for the people at home, or who are watching this late at night because of a lab. So B could be over here, or B could be over here, and that'd still be a legitimate binary tree. Naturally, C could be over here, or C could be down here. It's still a binary tree. Yes?
Is this kind of like parent classes and like super classes and stuff like that?
No. No, that's an OOP concept, which is something different. This is how we organize data. Oops. Hey, look, the other ways they just showed you. So these are still with 3 different nodes. Every node has at most 2 children. All right, great. We're going to fast forward. We're not going to talk about traversal right now. Okay. Let's go ahead and start talking about a binary tree. I don't think the slides do a good job about explaining why it's important. Hopefully this marker is clear. I can't even see it. Okay. terrible. All right. Yes! Oh, did the cap fall off? Oh, something. All right. See you guys. I'm going to join the NBA. All right. How about this one? It's better. All right, so we're going to leave. This one's okay. We need something dark. Oh, here's a black one. Oh, I bet that's a lot better.
There we go.
Okay, great. All right, everyone, give me some numbers.
5, 2, 3, 4. 54.
-22.
I always forget about the negatives.
45.
7,000.
You always forget about the negatives. All right. So if we wanted to put this into a binary tree, just a binary tree with no other stipulations, that it's simply a binary tree. One way to do this is we could go 5, 2, we could put 3 over here, 54 right over here, put -22 over here, and then we have 45. Oh, good. Ooh, there we go, 45, and then over here, 1,000. Now, naturally, these two guys have links coming out. They're going to null. I'm not going to write them because I don't want to write it.
Does it matter the ordering in which you put them into?
For a regular binary tree, no.
So you could start with 1,000 and then
Yeah,
skip
you
around
could
and then you go
switch
down.
all these numbers up and it's still a binary tree. But we're going to get to why that's bad momentarily. Because now I'm going to ask the question, if you need to find where 45 is, how would you do that? You have to search every node, which is terrible. So we're going to add a stipulation, and we're going to add a stipulation and then call the binary tree something else. What we're going to say is, if you're at a node, everything to the left of the node is less than it, and everything to the right of the node is greater than it. And this is going to be let me erase this first. And we're going to call this a binary search tree. So a binary search tree is a binary tree with that ordering operator I just told you about. So let's go ahead and move this camera up so people can see all the numbers. Yes?
So the first one, for the first one in the tree, then would you want like this in the middle of your data set?
So you're talking about the binary tree?
Yeah, because if you say everything to the left is less than, everything to the right is greater than, wouldn't you want it in the middle?
Yeah, you'd want to pick the middle one up top, but you can't always guarantee that. And we're going to get to that a little later. It's actually going to be your project about balancing it and whatnot, because that actually is a very complicated operation. But we're going to start back with just simple ordering. So let's go ahead and add these in the correct order of a binary search tree. Now, luckily, you can just add them one at a time, and it's still a binary search tree. It may have a couple other issues, but it'll still work out. So we're going to start with a 5. That's great. Now we need to add the 2. Does 2 go to the left of the 5 or the right? Left, all right. Okay, now we're at 3. Does the 3 go to the right of the 5? No, so we go to the 2. Does the 3 go to the left of the 2 or the right of the 2? Right, to the right. Because the 2 is less than the 5, but the 3 is greater than the 2. Okay, so notice that here, the only numbers that are going to be to the right are between 2 and 5. Okay? All right, so now let's go 54. Where's it going? Of the 5. -22. Left of the 2. All right, what comes next? 45? Oh, yeah, thank you for stopping me, whoever told me I wrote the exact wrong number, because I did. All right, now the 45. Left of the, is this where the glare is? Okay, no, we missed the glares. And where does the 1,000 go? Okay, y'all did not do this on purpose, but y'all did pick numbers to make this tree perfectly balanced, so good job. All right, now if you want to find the 45, what do you do?
Go to the 5, 45 is to which end? So 54, 45 is less than 54, so go to the left.
Right, so did you have to go and search these guys? No, you have to search these guys. All right, so what do you think the runtime of searching a binary search tree is? Well, hang on.
Log base 2.
Why is it log base 2?
It was just like binary search, where it's basically ordered by the. Basically, once you pick left or right, you cut out half the options.
Right.
Every single time.
So every single time you're cutting out half the options of what's left. Basically, a binary search tree is you're integrating that whole binary search into a data structure so that simply by traversing it or trying to search for something, you're doing essentially a binary search. Now, but here's another trick. How hard is it to add something? What's the big O of adding? Ooh, not O of N. Well,
O to the power line?
wow, we're just guessing here. Think about it. If we need to add the 1,000, we start at the 5. What do we do? Right. Do we just cut out half the search space? Yes. So log of n. So adding something's also log of n. All right. So we're going to let's go ahead and let's see. Let's go ahead and write this out to the right, since I think this is a good time. So we're going to do array, linked list, and a binary search tree, BST. Everyone good with those acronyms? Okay, good. Am I still on the board? Yes. Okay, so if you want to, now this is going to be a little tricky here. If you want to add to the end, what is that in an array?
Average of 1.
Yeah. So normally it's O of 1 or O of n. How about a linked list? O of 1. Binary search tree.
Let's take a look.
N is the size of the data structure. How many elements are in the data structure? So we did just talk about this, but that's okay. Remember, if you need to add the 1,000, you start at the 5, you go to the right, you just cut out half of the, yeah, so it's log of n. Yeah. This is going to be the pattern here, guys. I'm going to put the word balanced up here, and I'll talk about that in a bit. Ignore that for now. I just want to show you why this is so important. How about add front? For an array, it's always O of n because you got to shift everything down. Linked list, O of 1. Binary search tree. It doesn't matter if you're adding to the end or the front, it's just putting it. There's no, see, this is what's kind of tricky, is for a binary search tree, there is no adding to the end or adding to the front. You're just adding. So we're just going to call it log of n, because you can't add to the front or the back, you're really just adding it. So that's why I'm putting that in quotes, just to show you. Okay, how about searching? Here we go. You're searching for an element in an array.
Well, you could do binary search. It have to be
Right, so it'd have to be sorted. But if we were doing a sorted,
usually just
if you were doing sorted, these would be different, right?
Yeah.
So I'm going to put unordered, unsorted up here, because that's what we've been doing. So if you need to search an unsorted array, it's O of n. Linked list, it doesn't even matter. You have to, it's O of n, no matter what. And then binary search tree, log of n. Have you found the pattern with the binary search tree yet?
Yeah.
Okay, I'm gonna, Eli put out a good point. I forgot to put a sorted array here, so let's go look at that. When you add to a sorted array, what is it?
O of n, because you have to find where to put it and then shift the later elements.
Everyone see that?
Although it could be
Once you, so if you have a sorted array of 1,000 elements, and you need to add a certain element to it, there's no adding to the front or end, you're just adding. Let's say on average it's in the middle. Now you can find that position in log of n time because of a binary search, right? So that's log of n there. But in order to actually put it there, you have to shift all the other elements down, which is an O of n operation. and then add the element. So adding to a sorted array is always O of n. O of n, O of n, and then of course you can do a binary search for log of n. Okay, so who's winning? Well,
Or list of any if you want.
right, so which is the best data structure?
It depends.
Yeah, there we go, all right.
Favorite phrase.
Be careful, I'm gonna ask you this question many different ways. Because there is no best data structure here. But binary search tree seems to be giving you a really log-based n of everything answer. Okay, I'm going to erase this. Everyone okay with this so far? All right. Okay, now, what could happen with our binary search tree that would not make searching a log of n?
If you have them all on one side.
If you have them all on one side. So, in other words, if we decided to add these elements up there in a different order, like let's say for instance we first added 1,000, and then we added 54 for some reason, then we added 45, then we added, what would be next, 5, then we added 3, then we added 2, am I going off the board? Oh, definitely. Then we added -22. All right. What's searching now? O of n. Uh-oh. Okay. So your adding function, the way to fix this is when you add something to rearrange all the elements. We are not going to do that for our lab. That's going to be your project. That's project 3. There you go. Everyone, you got a preview of project 3.
Just sorting?
You're going to implement a balanced binary tree for project 3. You may have many different choices. You have to implement 2 of them. There's AVL, there's red-black trees, there's scapegoat trees, there's treeps. There are all sorts of balanced binary trees. It turns out to be a very interesting and hard problem, but we will get to that with project 3. We are not going to try and balance it now. Everyone got it?
Got it.
Okay. All right. So, let's see. What would y'all like next? Code. Oh, I had a feeling that was coming up. Well, before we go to the code, I want to do one last thing. Let me go ahead and write the binary tree up here. And I want you to think about if I wanted to, why am I doing it this way? If I wanted to print the elements of the binary tree, how would I go about doing that?
Start on one side and then on one side go to the other.
Start on one side.
So if it's balanced, you can like start the ones less than and then go to the ones, I guess. What are we trying to do?
I want to print out all the elements.
Any specific order?
Ooh, that's a good question. Yeah, what should be the order? Ooh, there's glare. A simple order. Okay, that's good. What do we got, 45? And then 1,000. Okay. How will we print this? Well, first off, are there different ways to print this?
Yeah.
Yes, okay, good. Recursion, yes. When you do binary search trees, if you write your algorithms recursively, it's going to be a lot easier. All right. So, well, first off, you probably want to set up the way you traverse. The standard way to do it is called a depth-first search, which is doing it recursively. You start at 5, you go to 2, you go to -22, you pop up, you go to the right, 23. Let me start over because I skipped something. Start at 5, go to the left, 2. Go to the left, -22, go to the left, there's nothing there. Go back to -22, go to the right, there's nothing there. Go back to -22, you visited all the children, go up to 2. You visited the left child, so you're going to go to the right child, 3. Go to the left, nothing there. Go to the right, nothing there. You visit all the children. Go back to 2. You visit all the children. Go to 5. You visited the left child. Go to the right child, 54. First start by going to the left child, 45. Go to the left, nothing's there. Go to the right, nothing's there. Visit all the children. Go back up. 54, you visit the left child. Go to the right, 1000. Visit. There's nothing to the left. There's nothing to the right. You visit all the children. Come back up. 54, you visit all the children. Come back up. 5, you visit all the children. You're done.
That seems very slow. It would be very slow.
Not quite. It's not that bad. I mean, it's still O of n because you visit every node. It sounds like a lot. Ends up being fairly easy. So the question is, when do we print the numbers?
After you visited all the children.
Okay, so we could do it, and that's called post order. Post order after you visit all the children. So what would be printed if we did it in post order? Oh, he said after you visit all the children. So you don't start at 5.
It'd be like 22.
Negative 22. 2.
3, 2.
Oh, I'm sorry, you're correct. 3. Thank you.
Why is that?
Because when you come up to 2, you've only visited the left child, you haven't visited the right child. So then that would be a 3. Because there's nothing there. Then the 2, you visit all the children, so it's a 2. Then you go up to 5, you haven't visited all the children, so you go to 54, haven't visited all the children, you go to 45. There's no children, so next would come to 45. And then what would be printed next?
1,000.
There, 1,000. 54. Okay. I'm going to tell you the other way. It's called in order. You print it after you visited the left child. So 5, you haven't visited the left child. 2, okay. So the first is the negative 22, because that's when you come back.
Oh, so you need
Yeah. And then you visit the right child, nothing there, pop up. You come back from the negative 22. You just visited the left child, so you print 2. You go to the right, nothing on the left, so now you've just visited the left child, you get 3. Visit the right, nothing there, coming back. You just visited the right child, so don't print. Come back, you visit the right child, don't print. Back to the 5, you just visited the left child, so we print the 5. Yeah, what's the next number? Now you go to 54, and then you need to go to the left child. 45, and then what's next? 54, 1,000. Hey, look. Hence why it's called in order. All right, so yes?
So if you want to print descent, you start on the right and just do the opposite. Just see if it goes to the right child first.
Oh, yeah. So if you want to do descending, you do it that way. Yep. Okay. All right, guys. So I've done post order, in order. What's the last one going to be? What? What was that? The new order? Mortar? Oh, Mordor. Oh, I liked it. Oh, that was good.
Just pre-order.
We got pre-order. There we go. Post order, in order. Let's go with pre-order. When are we going to do pre-order? The second you visit the node.
Oh, I thought it was at GameStop.
Huh?
I thought it was at GameStop.
GameStop? Oh, yeah. Wait a minute. So we visit 5, good. We visit the 2, good. We visit the negative 22, good. Nothing come up. Remember, it's,
Will we have to like check to see if it's already printed?
No. The second you visit the node, you print it, and then you go to the children.
Why would you go back up though? You're kind of.
Well, you're coming back. You're coming back from somewhere. So you've already visited the node.
Okay.
Yeah. So you have to keep track of that in a way, but it turns out to be really easy when we get to the code. 2, go to the 3. We're touching the 3, so of course we print the 3 immediately. Nothing to the children. Pop back up. What's the next number we would print out? No.
You print out 54.
54. Why do we print out the 54?
Because you've already printed 2, you've already printed 5, and you go to the right child.
Yeah. So then we go to 54. What gets printed next?
45.
45.
1,000.
All right. Okay. Great. I think it's coding time. So let's go ahead and pause the video and